Hello, my name is Chanugo and welcome to my presentation. This is a presentation video for Deep Learning course here at USC Viterbi School of Engineering. Today I am going to present my final project for the Deep Learning course, and the title of my project is Assume Guarantee Contract Framework for Formal Verification of a Neural Network-based Control System. The neural network have been successful in many application domains and they are everywhere right now. However, they are fragile because they exhibit unexplained behaviors sometimes and they are prone to input perturbations. And the list of those fatalities shows those. So can we actually guarantee or verify the safety or performance of a neural network, although they are exhibiting these unexplained behaviors? For example, on the right, this is a mountain car where you want to start on the bottom of the hill and would want to get to the goal position, or you don't want to hit the inelastic wall on the left. Can we actually guarantee these kind of specifications on this neural network based control system? So actually, verification of a neural network have been done by other people. So verification of a neural network, what does it mean? It means that you have to verify a property phi of this neural network. And people have been able to verify this input-output relationship of a neural network, where given a precondition on the input, the output guarantees a postcondition, and also robust classification of a neural network against perturbations, where given some allowable perturbation on the input, the classification of a result of a neural network does not change. But this becomes a little bit complicated once we get to a system with a neural network in a closed loop, a neural network-based control system. Because properties of a neural network-based control system is now no longer non-temporal. They are temporal, they might be temporal properties. So the properties that we want to prove or verify is that given some initial condition on the input of this closed loop system, the neural network based control system guarantees some post condition. For example, phi, given some initial car position at some range in this mountain car, it will eventually reach the goal position within some time step. And Berisic in 2019, using model checking techniques, was able to achieve such goal of verifying this phi, and they took 1,336 seconds to verify this, which was not scalable. So what we want to do here is trying to verify these neural network-based control system in a scalable way. And to do that, first, we verify a neural network using MILP technique. Second, we explore a monolithic approach, which is very similar to what Berisic is doing. And third, we finally introduce our novel compositional approach for formal verification of a neural network-based control system using assume and guarantee contracts. And then we present our result on case study. So first, let's start with verifying a neural network using mixed integer linear programming. We took the encoding technique from the paper in 2019 of encoding of the ReLU. And what we are doing here is that we iterate through all the ReLU or the neurons and get linear constraint from that. And if we get all the linear constraint from all the neurons and ReLUs, then we would effectively have a set of linear constraint that characterizes this neural network. So the approach we are taking is we are solving some kind of unsatisfiability problem using the set of constraint that we get from this this encoding. So what we are doing here is trying to find a counterexample that satisfies all the constraints from encoding that we did and violates the property phi. So the answer of this question means is that if there exists a counterexample, that it means that the neural network does not satisfy a property phi. And if there exists non-counterexample, that it means that the neural network actually satisfies this property phi. And then we went on and tried to verify the neural network-based control system in a closed loop using what we call a monolithic approach. So given the closed loop system and the neural network with plant and the system specification, we were kind of emulating the system in n steps by flattening this closed loop. And we are using the same approach as that we use for verifying the neural network. And for verifying this specification phi that we have been using, we were able to achieve 63.38 seconds compared to Verisix 1,336 seconds. Please note that we have different setups here because we have different number of layers, different number of neurons, and possibly different computing power as well. But we were able to achieve these results in our case. Moving on, so after that, we wanted to push it even further by using some more smarter way to verify a neural network-based control system. And we were using the compositional approach using the assumed guarantee contract. So let me go over a little bit on what assumed guarantee contracts are. So assumed guarantee contracts are basically a pair A and G which supports if then else style properties. A implies G, which means if the environment provides the behavior within the assumptions A, then the system promises a behavior within guarantees G. And the property phi that we have been working on can be written as a contract like this. But what's good about this contract is not that we are splitting this property to A and G. It's because these contracts facilitates compositional reasoning, where we can combine this contract using composition, and we can also replace one contract with another using the refinement relationship. And these has been proven very effective in some very complicated systems, cyber physical systems as well. So this is our approach given for compositional approach using the assumed guarantee contract. Given the system specification and neural network abstraction in contract format, and given the actual neural network and the plant, this is a two-step process. First, we check whether the given neural network abstraction is a correct or sound abstraction of the neural network. Second, we compose the abstracted neural network and abstracted plant and check whether this can effectively replace or refine the system level contract. And as a result, we would get yes or no answer. And in the no case, we would have a counterexample that explains why this neural network-based control system does not satisfy some system level specification. So for the case study, we were doing the mountain car. We trained a 3-layer neural network with 2 input and 1 output, and we wrote these 2 contracts, one for performance and one for safety. And we parameterized the time horizon for the guarantees as a 0 to tau in this case. So, and we also had to come up with the abstraction of the neural network. Here we were doing all these manually, but the approach that we took is first we are sampling the neural network policies within a feasible input space and created the under approximation of a feasible output space using polytopes. So for the mounting car here, the guarantee we wrote as a contract in the contract was that if you are in the region 1 of the input space, that you and the output would be go left, and if you are in the region 2, then you have to go right. And as you can see, all the abstraction have different shape and different accuracy of the abstraction. So the result for the specification that we have been working on throughout this slide. We were able to see over 20 times speed up for the compositional approach compared to Verisig. And then we kind of increased the range of the initial position of the mounting car. And what we are observing here are first, we were seeing up to 16 times speed up for the proposed compositional approach compared with Verisig. And what we are also seeing was the accuracy and shape of the abstraction actually affect the runtime. And also, we are seeing that monolithic approach is overall not that scalable for larger kind of problems. And then we went on and did verification for the safety contract C2. And here, instead of changing the initial condition, we were changing the tau to investigate the scalability for different tau. So first, we observed the number of variables, including the continuous integer and binary variables. And second, we're observing the continuous variables for different tau. What we were observing was that both of them were increasing linearly with respect to tau. But for the continuous variables, for the number of continuous variables, we were seeing up to 5 times less number. And for the number of constraint and the runtime for different tau, we are seeing the linear increase in the number of variables and constraints. And from previous slide, we know that the continuous variables were up to 5 times less than the monolithic approach if we use the compositional approach, and up to 2 times less constraint if you are using compositional approach. For the runtime, they were all increasing exponentially with respect to tau, but what we were able to see was that up to 100 times less or faster runtime for the same problem using compositional approach. And as you can see, the exponential growth in the runtime kicks in much later for compositional approach, which means a compositional approach is overall more scalable than just monolithic approach. So in conclusion, we were able to encode a neural network to a set of linear constraints and we were able to verify simple properties of a neural network. And then we also verified properties of a neural network-based control system in closed loop using a monolithic approach using MILP as well. And then we were proposing a compositional approach for verification of a neural network-based control system, which were more scalable. And then we also illustrate the effectiveness of the proposed approach on verification of a neural network controlled mounting car within the open AI gym environment. Future works includes generalizing, automating, and optimizing the generation of a neural network abstraction and exploration of more scalable encodings and computational methods other than MILP. Thank you.